Swayam Prabha. Digital India. Educated India.
Hello viewers, welcome back to the lectures on stability of slopes. In our previous 4 lectures, we started with the infinite slopes, and as discussed last time, infinite slopes are those slopes whose extent is very large. In general, they are the natural slopes, and the failure surface in those slopes were taken as parallel to the ground surface, and we had considered number of situations, number of conditions, and then we discussed how to analyze those slopes. After that, we started discussing about the finite slopes. Here it is a small extent of this slope. Finite means it is not that large. Generally they are man-made structures, and we had already have discussions on Kalman's method, where planar surface was considered, and our discussions were continuing on the planar failure surface. So, we continue with the same discussion. Last time we have discussed this planar surface. This is applicable in case of the material likes when the rocks are there, they are not isotropic materials. So, here there is an anisotropy, a bedding plane or a discontinuity or a fracture plane, and we have considered this. There was a water table also, and this dip of the discontinuity was alpha, angle of the slope was beta, and we discussed how to analyze this. The basic principle remains the same. We considered the weight of this wedge, and that wedge was having the weight was resolved into 2 components, normal component and the tangential components, and then we discussed how to find out the factor of safety. We also discussed how to calculate the limiting height, the maximum possible height for given angle alpha. We solved some example also, and then we discussed, we showed it how the height, the permissible height, the limiting height varies with the angle alpha, and you could see that somewhere near 45 plus alpha by 2 the minimum permissible height is obtained. Then we discussed about the tension cracks. In the field, tension cracks are found sometimes in the upper face here or sometimes in the slope itself, and the basics of the analysis was that we assumed this was the water table. The depth of the water in tension crack was ZW. Hydrostatic pressure variation will be 0 here, and at the base here it will be gamma W into this depth. So, the pressure variation was triangular in nature, and the resultant was V acting in horizontal direction. For this surface, for the inclined surface, we considered the pressure diagram which is having this ordinate same as this, because at any point the pressure, the water pressure in all the direction will remain same. So, we considered same pressure here, the hydrostatic pressure, that is gamma W into ZW, and at this toe we had assumed that it is draining freely. So, the pressure was 0 and we assumed a triangular variation. You may note here that it was our assumption that it is draining freely. If it is not draining freely here at this point, and if the drainage is choked, then you may have very high pressure here also. So, in fact, if I assume a hypothetical situation where the complete choking of the drainage has taken place, then at this point you are going to get pressure equal to hydrostatic pressure, that is gamma W into this height. So, this U was the pressure acting on this sliding plane, and then we consider the same thing. Weight of the wedge was acting in downward direction, its component were considered in normal to the sliding plane and also tangential, and then we found out the factor of safety. The tension crack could develop in the face. So, here also if it is developing at this place, then we can find out what is the factor of safety of this wedge. Today we are starting with the another case of the same slope. Here now it is reinforcement, the slope is reinforced with tension anchors. This is a very effective measure which is used to stabilize the slopes. So, here an anchor has been installed, rest of the things are same. This is the slope face having angle beta, and here this is the joint plane or the fracture plane or the bedding plane, which is having dip of alpha, and we are assuming the tension crack is developed. It is having the water pressure is V. I have not shown the water table here. So, here it is V. Same way at this inclined joint plane, the water pressure acting is U. I have not shown the complete diagram because it might have become very complex. So, U you can find out as I discussed earlier, V you can find out, W one can find out using the geometry of this particular wedge, and components of W now can be resolved, and the factor of safety can be found out. The additional force which comes into picture at this stage is the tension T, which is being provided by this anchor. So, this anchor, let us say it is inclined at an angle theta with horizontal. You can see here theta is with the horizontal, and the effect of this anchor will be it is providing force on this sliding surface. So, here it is increasing the normal component of the force. So, by increasing normal component, it will enhance the shear strength. So, let us say that T, this is the anchor and it is making angle theta. Now, you can resolve this force T also perpendicular to the plane of sliding and also tangential in the same direction with the plane of sliding, and then we can do the further analysis. So, resolving the forces along the bedding plane, similar to previous cases, weight of component will be W sin alpha, the component of the water pressure in the tension crack will be V cos alpha, and the component of the tension which is there in the anchor will be T cos of alpha plus theta. Let me explain it here. This angle I have taken theta. So, if I draw a line here, then this angle will be theta, and the joint plane is making alpha degree here. So, this joint plane will be making alpha degree with the horizontal. So, angle of the anchor with joint plane will be theta plus alpha. So, its component parallel to the joint plane will be T cos alpha plus theta, and in present case this component will be acting in opposite direction, in the opposite direction to the sliding forces. So, here it is negative. So, along the bedding planes, the total components will be W sin alpha minus T cos of alpha plus theta plus V cos alpha. Now, to find out the shear strength along the joint plane, we have to find out the force which is acting normal to it. So, the force normal to sliding surface will be W cos alpha. So, like it was W sin alpha. So, here the other component will be W cos alpha plus T sin of alpha plus theta. Please note down here the component, the normal component is adding to the normal stress. So, here it will be plus not minus, and the component of V will be minus V sin alpha, and U is acting against in the opposite direction. So, it will be minus U. So, the shear resistance because of this normal force will be, you know, the equation is tau is equal to C plus sigma tan phi, and then when you multiply it by area, this equation will be C into A, that gives you the force, total force C dash into A plus this normal force W cos alpha plus T sin of alpha plus theta minus V sin alpha minus U, this whole multiplied by tan phi dash. Here C dash and phi dash are the shear strength, effective shear strength parameters. Now, we can find out the factor of safety. Factor of safety is nothing but the available strength, the maximum strength which the sliding surface can offer. So, it will be C dash plus A plus this entire W cos alpha minus U minus V sin alpha plus T sin theta plus alpha times tan phi dash divided by the sliding force. So, it is W sin alpha plus V cos alpha minus T cos alpha plus theta. So, this is the final expression of the factor of safety, and here you can see in this equation, if you compare it with the previous equations, or if you take T is equal to 0, then what is T doing here? What is the anchor? What is the effect of providing the anchor? You can easily analyze using this equation. Now, due to force T, you can see in the numerator there is this plus term. So, this is increasing, but it should be only up to certain value of this theta plus alpha. So, the numerator in this expression, the numerator is being increased. At the same time, if you look at the denominator, there is negative quantity. So, denominator is being decreased. You are adding something in the numerator and you are subtracting something from the denominator. So, denominator reduces, numerator increases. So, there will be substantial increase in the factor of safety, but orientation of anchor is very important, because if you want to have this values as positive value, then theta plus alpha should be less than 90. If it is more than 90 degree, this quantity becomes negative. So, this becomes negative, this is also negative. So, you may not find any, or you may find very small increase in the factor of safety depending on these values. So, for positive sign, this alpha plus theta should always be less than 90 degree, and it can be shown that the optimal value, the maximum value of the factor of safety will be obtained when this expression holds good, alpha plus theta equal to phi dash, or you can find out the optimal value of theta, the inclination of the anchor with the horizontal will be phi dash minus alpha. So, if this value, if theta is equal to this much, then the optimal solution will be available. So, this is the factor of safety expression, and you can show, you can explain why there is so much increase in the factor of safety. Let us take an example. It's a slope here having rocks, and here is the joint plane or the bedding planes. The slope angle is 60 degree, height of the slope is 12 meter, and there is a tension crack which develops at the upper surface, and the depth of the tension crack is 4.5 meter. The shear strength parameters C dash and phi dash along this plane are 25 kPa and 37 degree. Unit weight of this mass is given as 26 kilonewton per meter cube, and it is given that the depth of water in the tension crack is 3 meter, and T the available the tension in the anchor is 400 kilonewton per meter length. Per meter length means whatever analysis we will be doing, in that analysis we will be taking 1 meter dimension perpendicular to the plane of the paper. So, per meter length it is 400 kilonewton. Now, we have to find out factor of safety for various values of theta. Theta is the inclination of the anchor with the horizontal. So, factor of safety expression is C dash A. It includes area of the joint plane of the sliding surface where the sliding is taking place, and also we have to find out the weight of the wedge and the water pressure in horizontal on the plane and also in the tension crack. So, expression of A can be easily derived here. A will be equal to alpha is the angle with the horizontal. So, H minus Z into cosec alpha into 1, that gives the area on which sliding is going to take place. So, H is 12, Z is 4.5 and cosec alpha is 35. So, you get area 13.08 meters square. The force V, it is because of the water pressure in the tension crack. So, that is half into gamma W into ZW square. This is nothing but the area of the pressure distribution diagram. So, half into 9.81 into 3.5 square, you get the force. This will be acting in horizontal direction. Also, the force on the joint plane will be area of the diagram again, and the perpendicular ordinate we had taken half gamma W into ZW, and the base will be H minus Z into cos of alpha. So, U will be half 9.81, ZW is 3, H minus SZ into cosec of 35, and then you get this value of U. T is already available, and we have been asked to find out for different theta values what will be the factor of safety. So, range of inclination of the anchor is within 90 degree. We will not allow it to increase beyond 90 degree. Above that there won't be any, if there will be rather the opposite effect, negative effect of the anchor. So, alpha plus theta can always be less than 90 degrees. So, theta should always be less than 90 minus 35. So, it can vary up to 55. Also, as I told you, the optimal expression is available with us. So, from that, for optimal value alpha plus theta should be equal to phi dash, and from here theta is equal to phi dash minus alpha, that comes out to be equal to 2 degree. So, now everything is available for that expression, and simply we have to put the values, different angles. I have calculated only few values 55, 30, 20 and 2, and you can see the at 55 factor of safety is 1.65, and here it is 2.1, 2.3 and 2.64. So, it is as the theta increases, if I go from downward to upward direction, the factor of safety is decreasing. So, here it is theta is here. So, you can see if it is almost horizontal, if this angle is very small 2 degree angle, then you get the very high factor of safety. If you rotate this anchor and go on increasing it, then you had seen that at 55 this is 1.65, And in fact, if you make it inclined further, if this anchor goes in this direction and T will be acting in this direction, so it will be adding, one component of this will be adding to the destabilizing forces. So we will not allow it to go beyond this angle, so 55 degree. Secondly, you can do the analysis using different ZW values also. See here, in the expression V comes into picture and V is because of this. So you can also find out what happens if there is a heavy rainfall and this entire crack is filled with water. So V will be maximum. Or you can also do the analysis if there is some if the drainage at this particular toe is choked, what is going to happen. So one can do the parametric analysis and then you can find out what are the variations of the factor of safety, how the slope is going to behave in different drainage conditions. Drainage conditions means, for example, if this is completely choked or it is completely free, or here the tension crack is filled with water or it is not filled with water, it is completely dry. So the extreme values you can find out and then you can have some plan. For example, during rainfall season some warning systems etc. may be designed. Here we have plotted the results of that analysis where we had varied theta. So you can see theta has been varied and for different values of theta, factor of safety has been plotted here, and as theta is increasing, as usual the theta is the inclination of the anchor. As theta is increasing, the factor of safety is decreasing. So similar kind of the analysis can be done for different parameters, for ZW or for the drainage conditions, etc. The planar failure surface, and now let us move on to the circular failure surface. Here this is an embankment or an earth dam, and this particular face there was sliding, and it has been observed that this surface is almost a circular surface. So in 3D it will be a cylindrical surface, in 2D it is a circular surface. So these kinds of the failures, they are called as rotational slide. Rotational slide means if the failure surface is circular, slide is called as rotational slide. Earlier we were discussing the planar slides. So here the surface is circular in 2D, and in 3D it will be a cylindrical surface. Here it is the center and this is the radius of the circle along which the failure has taken place. There are different categories of the rotational slides itself. It may be a slope failure, it may be a toe failure, or it may be a base failure. When we say slope failure, it means the failure has taken place in the slope itself, somewhere in the height, at this height itself, and it happens when the slope angle beta is high. Generally this is the angle beta, slope angle. This will happen when the beta angle is high and soil close to the toe is quite strong, or soil in the upper part of the slope is relatively weak. So if a composition of this slope, of this embankment, of this man-made structure is something like that, that here there is good quality of the soil, well compacted, having higher strength, very compact, very stiff, and at the top surface it is not that compacted, it is weaker, then failure can take place in the upper surface, and this particular failure is termed as slope failure. So here the slope is failing. In second case, toe failure. Toe means this point is termed as toe, this is the toe of the slope. Failure surface is again circular, but the circle now passes through the toe of the slope, and it occurs in steep slopes when the soil mass above the base and below the base is homogeneous. So, here it is almost similar type of the properties are there in this, in the embankment or in the dam, as well as in the base here. And this is the most common mode of failure. Most of the times this is going to happen. So, this and this slope angle, it should be relatively steep. For those steep slopes, generally this kind of the failure will be taking place. So, earlier the failure was taking place in the slope, now it is taking place through the toe. The third case may be there when we have stronger soil in the embankment or in the dam, and in the base here the soil is little bit softer. So, it is easy for the failure surface to penetrate through the base, and in this case the circle, the failure surface will emerge out of the ground somewhere here, which will be some distance away from the toe. So, it is not passing through the toe, it is a little bit away. So, this can occur when the soil below the toe is relatively weak and soft, and the slope is also flat. So, this generally occurs for the flatter slopes. Earlier two cases, they occur for steep slopes. The failure circle is called midpoint circle. So, in this case this circle will be termed as midpoint circle. Now, before we start the actual analysis, let me discuss some more points, some philosophical points. And first of all, I am taking the limiting equilibrium method and critical stages in stability. So, some discussions I would like to have on these, though some of these points we have already discussed. The limiting equilibrium approach means assuming a limiting equilibrium condition when the factor of safety is 1. So, this I have been emphasizing right from the beginning. There are different types of the methods available. So, the method which we are using at present is that we are saying, we are assuming that the system is just in equilibrium. It is just at the verge of failure, or the factor of safety is equal to 1. Now, second point, a surface of sliding is first defined, and the soil mass which is expected to move along this surface is considered as a free body in the equilibrium. So, here the first what we do is we consider a failure surface, whether it is a circular failure surface or it is a planar failure surface. We consider a failure surface, and the mass, soil mass which is above that failure surface, the mass which is expected to move along this surface is considered as a rigid body, as a free body, and we consider the equilibrium of that particular body. Now, the forces acting on the free body are then considered in order to evaluate the factor of safety. So, that body we consider as a whole mass, as a whole free body, and then its equilibrium is considered, and from that equilibrium then we decide the factor of safety. The stability is analyzed corresponding to two stages. This is specifically for the man-made structures, for the embankments, for the dams, earthen dams or rock-filled dams. We generally consider two extreme cases. First is immediately after the construction. Just after the construction has been completed, at the end of the construction we analyze the situation. And second is after a long time has elapsed since construction. So, second is after a long time. So, what is the difference between these two is immediately after the construction the pore water pressure, I mean to say the excess pore water pressure may be there. The excess pore water pressure may take time, it may take years to dissipate. So, there are certain soils in which case the excess pore water pressure may dissipate very quickly. In certain soils the excess pore water pressure may take years. So, immediately after the construction there may be very large, very huge pore water pressure. So, that has to be considered, and after a long time means now the sufficient time has elapsed, the excess pore water pressure which developed because of the additional loads that has dissipated. So, we consider both these situations, and the significance lies in the shear strength parameters that would become applicable in these two cases. So, the significance of these two cases is you have to decide which kind of the shear strength parameters you have to use for these analysis. For free draining soils like sands or even coarse silts, effective stress shear strength parameters are used in both the end of construction and long term stability analysis. So, this is what I was telling you. If it is a geological material like sand, gravel, or even if it is coarse silt, what is going to happen is within very short time the excess pore water pressure which developed in the soil mass is going to dissipate, or you can say there is no development of the pore water pressure. So, in those cases effective stress shear strength parameters are used. So, it is very important. So, if there is the soil like sands, then effective stress parameters are used for both end of the construction means just after the construction, and long term stability means after several years. So, for both those two extreme conditions we shall be using, we should be using, or we will use the effective shear strength parameters. But in case of cohesive soils with low permeability value, and in case of the cohesive soils, what happens in case of the cohesive soils is they are impermeable, the permeability is very low. So, undrained strength analysis is used for short term stability, means just at the end of the construction period the pore water pressure will be there, undrained strength has to be used, because we should use that method which is truly reflecting the field situation. So, here the condition will be undrained situation. So, undrained strength analysis should be done, and for the long term stability means after several years of the construction the stability of the structure of the embankment has to be checked using effective stress analysis. For fully saturated clay soil under undrained condition, that is immediately after the construction, the analysis which we use is also called as total stress analysis. So, here total stresses are used, not the effective stresses, and it is known to you that phi u, undrained phi value is taken as 0. If it is over consolidated clay, in that case effective stress analysis is used for short term as well as long term stability. Over consolidated clays are a little bit different case. They have been consolidated more than what they are being done at present. In the past they have been over consolidated. So, for them effective stress analysis is used for short term as well as long term stability, but instead of using the peak shear strength parameters, the residual shear strength parameters are used in the analysis. These are important points which we have to remember. Now, some discussion about the total stress and effective stress analysis. These are the terms which I have been using. Total stress analysis, it is based on total stress and not on effective stress. We have already discussed what is total stress. Effective stress means after subtracting the pore water pressure stresses. So, it is based on total stresses. We take into account the total stresses. It is assumed that the pore water pressure developing on a slip surface are simulated while determining the shear strength parameters using laboratory tests. Our assumption in this case is that when we did the laboratory test to determine the shear strength parameters, all those conditions of the pore water pressure, the pore water pressures were properly simulated. This is our assumption, that in the test itself pore water pressure was there, but unfortunately this assumption is not really valid. So, we have to keep it in mind. In case of effective stress analysis, the analysis is based on effective stresses, on effective shear strength parameters and effective stress. We consider C dash and phi dash, not C phi, and also we take sigma dash. The effective shear strength parameters are not very sensitive to test conditions, and therefore, such a strength determination is quite dependable. In fact, as in the previous slide we told you that in case of the cohesive soils, the test conditions, we were assuming that the pore water pressure conditions are completely simulated. That is not possible. Rather, this is more reliable, that the effective shear strength parameters which we get, they are not very much sensitive to test conditions. So, their value is much more reliable. C dash and phi dash are determined in triaxial shear test by using consolidated drain test. So, these tests are common. You can find out C dash and phi dash using the triaxial strength test, triaxial shear strength test by using consolidated drained test. And for this analysis, because we are not assuming the pore water pressure to be simulated in the laboratory test in the values of the shear strength parameters. So, it is essential that in the field pore water pressure should be known. So, this effective stress analysis then will be much more reliable. It is convenient to use effective stress analysis for the situations, number 1, where pore water pressure does not build up at all. So, for example, this was the case which I discussed. If you take an example of sand, gravel, and maybe in some cases the silts also, if the pore water pressure is not developing, then effective stress analysis should be used. It all depends on the rate of application of the load and also rate of dissipation of pore water pressure. So, for example, this analysis, effective stress analysis, can be used in case of the silts provided the rate of loading is slow. So, if the rate of loading is slow, what is going to happen is there will be some rate at which the dissipation of pore water pressure, excess pore water pressure must be taking place. So, if this loading rate is slow and the dissipation rate is higher, it can be considered as drained situation. So, in that case also this effective stress analysis is used. Secondly, it is used where pore pressure at failure is a function of hydraulic conditions alone and could be obtained accurately, say by drawing the flow nets. So, this is important point. We are accounting for the pore water pressure separately here by using the effective stresses. So, in the analysis we should be able to input, we should be able to calculate the pore water pressure accurately. So, this is the situation where pore water pressure at failure is a function of hydraulic condition alone, so that we are able to calculate it accurately, for example, using the flow nets. In other words, we have to give an accurate value of the pore water pressure which is going to develop in the field. So, these are the situations where the effective stress analysis can be used. Now, let me come to what are the different types of stability analysis procedures. We divide them in two broad categories. One is the mass procedure and second one is the method of slices. Mass procedure means the mass of the soil above the surface of sliding is taken as a unit. As we discussed earlier, we are using the limit equilibrium approach. We will be assuming a circular failure surface, and above that circular failure surface the entire mass will be treated as a free body. So, in this first procedure we are treating the entire mass as a whole, and by taking it as a whole then we will be doing the analysis. In the second method, the method of slices, the soil above the surface of sliding is divided into number of vertical parallel slices. So, this method you can say it will be much more accurate in certain situations. So, here we are not going to take the mass as a whole, we will be dividing it into number of vertical slices to make our result, to make our analysis more accurate. First, we are taking the mass procedure, means the entire mass is being taken as one body, and here we are taking up the case of homogeneous clay under undrained conditions. So, phi u is equal to 0. Undrained condition means it is fully saturated clay, there is no drainage is taking place, and assumptions in the fully saturated clay under undrained conditions are that phi u, the undrained phi u value should be is taken as 0. The other assumptions which we will be using in the analysis are that the soil is homogeneous, we have been using this assumption many times, and also this shear strength parameter Cu is same at all the points along the surface which we have assumed, and thirdly the potential failure surface is being assumed to be circle, a circular failure surface. So, this is the slope here, this is angle beta, slope angle, and we have at present taken a case of toe failure. We have already discussed the conditions of the toe failure. It happens when this beta is relatively steep. You can remember here for these kind of the soils, if it is more than 53 degree, the toe failure will take place. This is the center O, and we have taken a trial circle AB. This is the circular surface, and the wedge which is trying to fail, which is trying to rotate, it is a rotational slide. So, which is trying to rotate is A, C, B and coming back to A. So, this is the wedge which is trying to rotate, which is trying to fail along this circular surface. The CG of this entire geometry can be found. You can use either graphical method or analytical method. You can find where the CG is acting. So, along that the weight W will be acting in downward direction. Here O is the center of this trial circle, H is the height. So, if I take this distance as L0, this is the W is acting in vertical direction. So, on the W, if I drop a perpendicular from O on the line of action of W, this is LO. So, it gives me the moment being generated by W. So, the actuating moment will be equal to, you can find it out for that trial circle, W into this L0. So, what we are doing is we are taking a trial circle, we are then finding out the total weight of this mass, and then we are calculating the actuating moment, that should be equal to W into L0. And what is the resisting moment? So, the resistance by the soil is being offered all along this circular surface. So, here the resistance is being offered, and at any point on this periphery, the direction of the resistance, if I take this point, it will be tangential to the circular surface. If I take this point, it will be tangential to the circular surface. If it is here, tangential, maybe horizontal, it is little bit in upward direction. So, at every point it is tangential. So, you can find out the sum of moments of all those small forces which I discussed. So, the resisting moment will be L A into Cm. So, if L A is the length of this arc. So, if you know this length of arc, which you can get analytically very easily based on this angle theta, you have already taken a trial circle and this angle subtended at the center is 2 theta, radius is r. You can find out this length of the arc. So, length of the arc and multiplied by the cohesion, this is the mobilized cohesion. So, that gives you cohesive force. So, this force is acting all along the periphery and its lever arm is R. So, the resisting moment will be L A Cm into R, where L A is the length of arc and R is the radius. So, when it is in equilibrium, at limit equilibrium, this actuating moment and resisting moment, they will be same. This is our assumption in limit equilibrium method. So, L A into Cm into R will be equal to W into L0. From there you can get the mobilized cohesion. Cm will be equal to W into L0 divided by L A into capital R. So, from this expression you can get that mobilized cohesion Cm, which is required to keep this slope in stable situation, just in limit equilibrium situation, and factor of safety is defined as tau f upon tau, or in terms of Cu and Cm you can define the factor of safety is always the maximum value of the cohesion which can be offered by the soil mass, and what is the value that is being used, that is being mobilized to keep this slope stable. So, Fs will be equal to Cu upon Cm. This Cu will be available from laboratory's test and this Cm will be available from this equilibrium condition, from this mechanical analysis. So, we will be able to find out the factor of safety. This factor of safety we found for one trial circle. So, this above procedure is repeated for several trial arcs, several circles we have to assume theoretically, as it will be very large number, and then we have to find out the minimum, we have to find out that circle which gives us minimum factor of safety, and that will be considered as critical circle. So, you can see the method is quite tedious, you have to take large number of these circles. So, the exercise has been made simpler by offering the graphical solution. So, here is the graphical solution which is available. This is the slope and the parameters of the slope as I discussed. This is the case of the toe failure. So, for critical circle you can directly find out some parameters. If I take this slope here, this angle is beta and this AB line is making angle alpha, and here this is an isosceles triangle A, B, O, which is subtending angle 2 theta at the center. For given beta values, here you can see 50, 60, 70, 80 and 90. For given beta values, these theta and alpha can be found out from this graphical solution. So, here on the y axis these are alpha and theta values, and you can see they are starting from 50 degree. In fact, in this situation the toe failure takes place when this beta is more than 53 degree. So, for example, suppose beta is 60 and you can go all along this line, it intersects the alpha curve somewhere here. So, you can read this value, it is somewhere between 30 and 35 or so. Same way this theta it is intersecting 60 degree line here, it is slightly more than that. So, somewhere around 38 or so. So, corresponding to this beta you can get alpha and theta. Once those values are available, then you can draw this line AB, you can then draw this triangle, because this angle is 2 theta. So, if you can very easily calculate this angle because this is 2 theta and it is an isosceles triangle. So, you can draw this ABO, and once this center O is available, you can very easily then find out the circle. You can very easily draw this geometry and you can find out W and you can do rest of the analysis. This is the graphical solution for base failure. In case of the base failure, this is the firm base and the circle is touching this base tangentially. So, here this radial vector will be vertical. So, and this radial vector will be intersecting this slope face at its midpoint. So, from a midpoint you can take this vertical line, and somewhere on this vertical line, somewhere near this vertical line, the exact critical circle will be there. And these are the parameters in this graphical solution. Please note it, there will be different parameters in different graphical solutions. This is h is the height of the slope, and this is the firm base. So, it is nd times h from this crest of the slope. So, this is nd into h, this is h, this parameter is x, this distance is x, this is nx into h, and here it will be b by 2 and b by 2. So, these values can easily be obtained using this graphical solution. Here beta is given, so corresponding to beta, and here are the nx values are available. Nx is equal to 0, 1, 2, 3, and here depth factor nd is available. So, using this graphical diagram you can find out the critical circle and then you can do the analysis. So, today we started with the reinforced slope, then we had some discussions, general discussions, then we started the circular failure surface, and on the next turn we will continue with the same analysis. Thank you.